This is the Logic Tutor. Welcome to the Logic Tutor. If you're new here, please click on the subscribe button, and if you are old, thanks for coming back again. This video contains alternative to practical for GCE candidates, and in physics precisely the subject. And we're going to look at two practicals. So possibly we're going to draw the graph for the two practicals, and we need to explain how alternative practical is being performed. When I mean alternative to practical, what does it mean? In the laboratory, either physics or chemistry, when we perform experiments, we get some kind of results or readings, especially as far as physics is concerned. We take readings from our experiment, and the readings which we use in plotting of graphs, in calculation, and so on. The slope of the graph can be used for various calculations, and so on. But here in alternative to practical, you are not going to do that practical physically. In practical aspects, you will get your diagrams, you have the apparatus, you will arrange the apparatus to suit your diagram. Then you carry out the experiment according to the given procedure, so you would be able to achieve the aim, get your readings and tabulate them, evaluate whatever you might be asked to evaluate, then plot necessary graphs and get your final results and calculations. But here in alternative to practical, the experimental setup will also be given to you in diagram in some cases, and your readings, which you are going to take either from an instrument or from an apparatus, will also be in form of diagram. So what I'm saying in essence is that you are taking your readings from diagram. Alternative to practical is so simple compared to practical because all the readings and let's say your table will all be generated from diagrams. So you need the ability to study diagrams and get them well. That is just what you need to get this physics practical done. Your diagrams are there. Take note of every information on the procedures available. Then the diagram. Study most especially the diagrams very well to get your readings. So we are going to look at mechanics and probably optics, because physics practical comes in a task where we have 4 branches, as I said, at secondary level. We have the mechanics, we have electricity, we have optics and heat. The exam comes with 3 questions from these 4 branches. So there are some branches that are certain, you will certainly get them in the exam. We have the mechanics, which is always the number 1 question. The number 2 question varies. You can either have optics or heat. Optics or heat. But electricity, which is the 3rd question, is always certain too. Every year you should always prepare for electricity and mechanics. But the tendency that you have optics is higher than heat as far as previous exam is concerned and various years ahead. You should have 64% chance of getting your optics, 60% chance of getting your optics, then you have 40% chance of getting it in your questions. So, but however, you are meant to answer just 2 of these questions in the physics practical. So we are going to look at optics and mechanics in this video. So I think you follow up this video as we're going to be doing the experiment and plotting the graph now. Okay, let's look at this question on 1998 practical physics, which is mechanics. We have the diagram given to us here as it is here. So they said in the diagram above, a meter rule whose center of gravity is G. According to the diagram, the center of gravity G is here. Is suspended from a steel needle. This is the steel needle, which is embedded into a cork and pinned by what? Pinned to the what? Meter rule. At a point P, this is particular point P, the distance h between the distance h between G and P, meaning the distance between the point P and the center of gravity, is determined and recorded. So the meter rule is slightly displaced. Can you see? It was displaced a little bit for it to move like a pendulum. So sideways and release to set it into oscillation in vertical plane. So the time t for 20 oscillation and the period t of oscillations are determined. So we are determining the time t for oscillations, for 20 oscillations, and we determine also the period of each oscillation. So the value of t square h and h square are evaluated and recorded. So the experiment is repeated for other values of h. So that means we are going to have varying values of h. So of different values of h, that means the distance between what? The center of gravity and P. So let us look at, we are going to make our table. H, we are measuring h. What else are we evaluating? We have h square. We are also calculating the time taken for 20 oscillations. Then we also have the period. Then we also have the period square. Then we have the period square times h. So these are the values we are meant to plot in our table. So let us make sure the unit is there. This is centimeter. This is centimeter square. Time is seconds. Period is also seconds. Period square is also second square. So this is the product of period square, that's second square centimeter. So if that is the units for this. So this is a table of our value. So don't forget that this period to calculate is equals to the time taken for 20 complete oscillation over number of oscillation. Don't forget, number of oscillation is 20. We are concentrating on 20 oscillations, so we have h. Now let's go. As we have said earlier, the readings is going to be taken from diagrams. So the experiment which has been performed, what are we asked to do? So we are going to look at the experiment is repeated for the values of h, and all these values are determined and recorded. In this particular figure, 1a and 1b, this is 1a and this is 1b. This 1a shows us the respective height that was given to us, and this is the time measured. We are going to take our readings all from here. So now, as we go, let's complete the instruction. Show the distance hi, that's those diagram, and the corresponding time ti, respectively, where I represents numbers. That means the first one, the second, third, up to the fifth. So determine and record the real value of h, the real value, because those values here, once you measure them, they are drawn to scale. So as you can see, there is a scale here that says 1 centimeter represents 10 centimeter. So whatever value you measure here, you are still multiplying it by 10 to get the real value of h. So after doing that, real value of h and the corresponding value of t, we are also going to measure at h1 to g, what will be the time at t1. We measure like this. So from there, we are to determine the following t square h and a squared, and tabulate our reading, which I've already prepared the table. So then plot the graph of t square on the vertical axis and a square on the horizontal axis, starting both axes from the origin. So let's take this into consideration and take our values for h. So for h, for the first h, I place my ruler at this particular point to take my reading. I measure the value So I can read 3.6. So 3.6 multiplied by 10 is going to give me 36. So I'm having 36.00. Make sure your recordings or your records you're taking is at least 1 or 2 decimal places for standard WAEC marking guide. So let's go to h squared. We evaluate h squared, that is 36 squared, which gives 1296. 1296.0. So let's take all the readings, then from there we evaluate whatever we want. So let's take for H2. Then I bring down my meter rule a little bit. I've left H1. So let's measure from H2. So I'm having 3.5 now. No, I'm having 3.3. This 3.3, which is what? 33.00. So then I go to H3 to take my reading. I'm having 2.7. 2.7, that will be 27.00. Multiplying by 10 to get the real value, since the scale is 1 centimeter to 10 centimeter. So I go to the next one, which is the fourth one. I take my readings. So I have 2.123, that's 23.00. Then the last value, I have 1.9, which is 19.00. So these are the values I got. Now let's look at the time at this particular point before we evaluate others. We're also going to look at the time. So how do we measure the time? We have T1. We are measuring from here, since time is what? Is anti-clockwise. So now let's pick it from here. Each distance represents, if you look at it, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 up to 1. So that means each gap is 0.1. So this is from here, we have 30, that's 31. From here to here to here, that means we are going to have, this is 32, then we have 32.1. That's 32.10 seconds. That's our T1. So let's go for T2. We measure all the way from here. So this is 31, and we also have this. So this is 31, 31.1, 0.2, 0.3, 0.4, 0.5. So we have 31.50 seconds. Then we go to T3. This is 30. That will be 30.9. 30.9. So which happens with, and this be 31. So we have 30.90 seconds. Then go to T4. We have 30.1, 2, 3, 4. We have 30.40 seconds, and here we have 30.4, 0.5, 0.6, 0.7. So we have 30.70 seconds. So let us evaluate the table to complete it all. So I have 33 squared, that gives me 1089. 1089. So from there I have 27 squared, so that gives me 723. 723.0. Don't forget 0.0. So then the next one I have 23 squared, which is 529. 529. Then lastly we have 19 squared, which is 361.0. So to evaluate the period, we know the period is time over number of oscillation, which is 20. So we have time, which is 32.10, so I have 32.10 divided by 20. That gives me 1.605. 1.605. So I have 31.50 divided by 20. That gives me 1.575. It's already in 3 decimal place. So we have 30.90 divided by 20. That gives us 1.545. Then we have 30.40 divided by 20 to get our period. So we have 1.52. Then we have 30.70 divided by 20. 1.533, which is almost close to this. So now we evaluate t square. We square the values here. So we have 1.605 squared. So that gives us 2.576. 2.576. The second one gives 1.575 squared. That gives us 2.481. 2.481. Then I have 1.545 squared. That gives 2.387. 2.387. So I have 1.52 squared. 2.310. 2.310. Then I have 1.533 squared. So that gives 2.350. 2.350. So as we have gotten these values, we can evaluate t squared multiplied by h. T squared multiplied by h. So let's multiply this with this. So we have 2.576 times 36. So that gives us 92.74. 92.74. So we have 33 times 2.481. 2.481. That gives us 81.87. And we also have 27 times 2.387. So that gives 64.45. So we have 23 times 2.310. So that gives us 53.13. Then we have 19 multiplied by 2.350. So that gives us 44.65. So we have tabulated our readings. Our readings has been taken from here and we have make the tabulations. So the rest of what we're going to do is to plot the graph. And don't forget, the graph must be titled. So we are plotting the graph of, according to the question, we are plotting the graph of t square on the vertical axis and a square on the horizontal axis. So this is the vertical axis and this is the horizontal. So to choose our scale, our table of value will determine which scale is best to be used. So scale choosing is one of the a technical point in plotting of graphs. So but firstly, your graph has to be titled. So we are plotting the graph of t square h against h square. So the one on the vertical axis is against the one on the horizontal axis. So how do we choose a scale for the vertical axis? So we have 92, we have 44, we have 53, we have 64, 81. So that means it's a range between 40 to 100. So we can choose a scale in such a way that all these values will be easily picked from the graph. So, and we have each boxes here, each big box here represents 2 centimeter as per graph. So if I say 2 centimeter represents 1, it means this big box from here down to here on the vertical axis represents 1 unit. 1 unit. So meaning that we have 10 more boxes in it. This 2 centimeter is divided into 10 more small boxes. So meaning that that's 1 unit divided by 10. Meaning each box in it is 0.1, 0.1, 0.1. So but if I decide to use the scale of 2 centimeter to 10, it means that each box contains 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then goes again 2 centimeter to 10. That's making 4 centimeter, that will be 20. And I have a range starting from 40 to 100. And you have to plot your graph in such a way that you cover at least 70% of your graph notes. It's very important. So if I use a scale of 2 centimeter to 20, let's assume I leave a line for the horizontal and I have 20, 40, 60, 80, 100. As you can see, the 100 does not cover up to 70% of the graph. So I can decide to use 10, 20, 30, 40, 50, 60, 70, 80, 90, then 100. So I can see I've used up to 70% of the graph. So meaning that my vertical axis, I'm using the scale of 2 centimeter to 10 units. So meaning each small boxes in it is 1. So having known this, I'll get my ruler and place a line to represent my vertical axis. Then I place one to represent my horizontal axis. The origin of the graph starts from here, 0, 0. Then I'm plotting t square h on the vertical axis, so I'm having t square h, and the unit is second square centimeter, and h on the h square, so I'm having centimeter square here. So already I have decided to use on y-axis. That is not going to be called y-axis, it's going to be called t square h axis, because it's not y. Y is not a variable we are actually plotting there. So we have the scale we use should be stated. So t square h axis, I use a scale of 2 centimeter to 10 centimeters, second square centimeter. So meaning from here we have 10. But please, let's make it into decimal place. 20.00, 30.00, 40.00, 50.00, 60.00, 70.00, 80.00, 90.00, 100.00, and that would be 110. So due to the table we have this. So let's go for the plotting of our h square. H square I have 360 or thereabouts. So that means the range is between 350, or let's say 400 to 1300. So that is the range. So which scale will I use that I will be able to read out all these values? Though I'm going to make use of their approximate value, but I'm going to make use of that scale. So if I use 10 centimeter to represent 100, I will have 100, 200, 300, 400, 500, 600, 700, 800, 900, and I have 1000. So meaning that my line is not supposed to be here, it's supposed to be on this place. So if I have 100, 200, 300, 400, 5, 6, 7, 8, 9. Okay, I can decide to choose another scale. I can use 2 centimeter to represent 200. So if I have 200, 400, 6, 8, 1000, then 1002. Then I have 1004. I think that is still acceptable. At least I covered 70% of the graph on the horizontal axis. So if I use 2 cm to 200, it means each boxes will be 200 divided by 10. So each boxes will be 20. So I'm using 200.00, 400.00, 600.00, 800.00, 1000.00, 1200.00, 1400.00. So let's stop there. So let's pick our values and go along with it. So we are having 36 on h squared. Oh, we are having, yes, we are having, I mean on h squared, we are having 1296. This is 1200 here. So 296 is going to take like how many boxes more? Each one is 20, so this 1220, 1220, 1240, 1260, 1280, 1002. This is 1300. So that means 1296 will fall around this region, the middle of this region, and it goes to 92.7, so which is approximately 93 or thereabouts. So I'm using the approximate value 93. So if I trace that up, starting from here, if I trace that up, this is 80, 90, so I'm going to 92, that will be 90, this is 91, this is 10, so 91, 92, so 93, I can let it fall here, around this region. Then I go again for 1089 to 181, that's approximately 82. 1089, so this is 1000, 1020, 1040, 1060, 1080. So 1089 will be around this region. 1089 will be around this region on this line, and it goes to 81, or let's use 82 to be precise. So this is 70, this is 80, so this is 81, 82, it should fall around this region. So we go again to 723, goes to 64.45, so which I'm going to use 64. I'm going to use 64. So we have our 64.5, that means halfway of 64. So then we have 723. So 700 should be before 800. So I have 620, 640, 660, 680, 700. That's 700. I have 723. So this is 720. So the 723 should fall around this region, very close to that line. So I take it up to 64. This is 50, 60, 61, 62, 63, 64, and it's 64.5, so I can raise it up a little bit on that line. So then I go again, I have 529 to 53. 529, so we have 500 here. This is 520, 529 should be around this region, so on this line. So I trace it up to 53. 529 should be around this region, so I trace it up to 53. This 50, 51, 52, 53, so it's around this region. Then next I have 361 to 44.6. let's say 44.5. 361, this is 361 should fall below 400. So this is 220, 240, 260, 300, 300, 320, 340, 360. So 361 should be on this line, and it goes to 44.6. So let's find our 40. This is 40, 41, 42, 43, 44.6 should be around this region. So then I've taken all points. Then let's look at the fittest line, the best fitted line. So let's look at this. This goes this way. It touches 2 points. So let's look at this line. I think this is the best fitted line, because if we are going to have 2 points that overlaps the line, then one should be spread across the line, one should be on the other side, one should be at this side. So I think we have that. I think we have that now. If I draw this straight more, okay, yeah, I have this. Please avoid double lines on your graph. It's very important. So this is the graph, and I have 2 points that is half. This one is into the point a little bit, and the 2 points that is out of the line are spread across sides. So which shows that we are about 80% correct. So now let's move ahead to the graph. We are meant to determine the slope of the graph and the intersects C on the vertical axis. So we have the intersect at this point. So this is 30, 31, 32, 33. This is 33.5. I have 33.5 here. So the intersect C, we have the intersect C, intersect C is equals to 33.50. So now that will be in centimeter. So then we go again to find the slope of the graph. I advise you use a bigger slope. So if I start from here, and it goes this way, here will be change in t square h, and here will be what? Change in h square. So the slope of the graph S is going to be what? Change in t square h all over change in h squared. So from there, let's read the value of this. So the first year we have 81. This is 81, around 81. 81, that is x, that's change in t squared 2 minus 1, so we have 40. All over, we have, this is 1, 2, 3, 4, 5. So this is 20 times 5 is 100, so that's 1,100 minus, let's go for this, 1, 2, 3, 4, 5, 6, 7. So that's 20 times 7. 20 times 7. So that's about 140. 140. So subtracting this, I have 41 all over 1,100 minus 140. So that gives 960. So the slope S of the graph is 41.960. So which is 41 divided by 960. So that gives 0.0427. 0.0427, or we approximate in 3 decimal place to be what? 0.043. That is the slope of the graph S. And what else are we asked to do? So we were asked to what? Find the value of K1, which is 4 pi square over the slope, where pi is 22 over 7. So that will be K1 will be what? 4 pi square all over 0.043. As we all know, pi is 22 over 7, which is 3.142. So we have 4 times 3.142 squared over 0.043. So we have 4 times 3 points. Okay, let's check 3.142 squared. That will be times 4. So that gives us 39.4887 divided by 0.043. So 39.4887 divided by 0.043. So that gives me K1 equals 918.34. And we also meant to evaluate K2, which is equals to square root of C over S. And our intercept is what? 33.50. So where we have square root of 33.50 all over 0.34. So evaluating what is under its roots, I have 33.5 divided by 918.34. Then the square root of our answer, 33.5 divided by 918.34. So we have 0, the square root of 0.0365. So we have square root of 0.0365. So that gives us K2 equals 0.191. So this happens to be the end of what we are asked to do. Now we have state 2 precautions you would take if you were to perform this practical or the experiment in the laboratory. What are the precautions you are going to put in place? It is very okay. I ensured I would have, if you perform the experiment, you say I ensured. But by the time you are not the one that performed the experiment, you took your readings from diagram. So then what you would say is, I would ensure or avoid parallax error in using the meter rule. So you have to mention that instrument you are making use of which you will avoid parallax error. Then I ensure the cork is held tightly in order not to disturb the 20 oscillations. I ensure the stopwatch is stopped immediately after 20 oscillation is complete, and many more precautions that you need to take. So that is for that. Then use your graph to determine the period T of the oscillation for which distance h equals this. So we can easily do that. We should use our graph to determine that. So here we have use your distance, use your graph to determine the period T. Using the formula, I have h equals 10 root 10. H equals 10 root 10. So and we are meant to determine the period T from the graph when the distance is h squared. So it is very simple for me to do that. I know that h equals this. Don't forget s, we are using the formula s equals change in t squared h over h squared. So now when my h is this and my slope is 0.043, and which is that my graph, 0.043 is equals to change in t squared multiplied by, or let's say t squared over change in h. So if we say this go with this go with this, then our h is 10 root 10. So we have, let's just write it, 0.043 equals 10 root 10 h squared over h 10 root 10 t squared, I mean, over h squared, which is 10 root 10 squared as well. So from there, I can have 10 goes here, I have 10 root 10, 0.043 equals t squared over 10 root 10. So 10 root 10 multiplied by our slope, 10 root 10 multiplied by the slope, which is 0.043, gives t squared equals 1.3597. So square root of that, square root of 1.3597. So that gives us, the period is going to be what? 1.166 seconds. So this is the second practical on optics, and it's a question of the year 2004. So we're going to practice this as well and look at how it is done. So here we have the diagram. The diagram is set up, and this is where we're going to take our readings from. So I have a ray box here, and an object X is attached to it. So the principal foci P, this particular point is what is called principal focus. The principal foci P and Q, foci is the plural form, so we have two principal focus, which is P and Q, of a converging lens. This is a converging lens. Convex lens is a converging lens. We're determined. That means we are meant to determine that principal focus. The image of an illuminated object O placed at distance m from P. This is object O. This is X is the object O placed at distance m. That's the gap between the object X and P is what is m. From P is obtained on a screen S. Is obtained on a screen. That means the image is obtained here at a distance n from Q. That means the gap between the image and the second principal focus is n, as shown in this diagram. So the procedure is repeated for a various value of m. That means we are going to be shifting the objects closer to P, that means or away from P, to get various values of m according to the experiment, but we are not performing the experiment yet. So as shown in the diagram above, the procedure is repeated for various value of m, and the corresponding value of n were to be measured and recorded, because whatever value you give to m will determine the value of n, because it is an image formation techniques. If I shift this backward, the distance m has increased, then the lens will take the objects and the image will be formed on the screen. So the gap between the value n, the gap between S and Q will also vary as n varies. So the procedure is repeated for a various value of m, and corresponding value of n we are measured and recorded. So the values we are measuring is what? Is m and n. They are both in centimeter. So at the same time, we have in this figure POI. This is POI. I mean, this is the figure P and this is figure Q. So represent the distance MI. I represents numbers, the first, the second, the third. So, and we have the corresponding value of n at that particular point. So the gap between P and the first object, this is the m. So the second one will be from here to here. That's another m, m2. This is m1, this is m2. From here to here will be m3, 4, 5, and 6. So corresponding value of the image, which is n, distance of the image from the principal focus is, this is S1, the longest one, S2, S3, S4, S5, and X6. So we are meant to measure and record the value of m and the corresponding value of n. So we are going to measure we take our readings from here, and don't forget all these diagrams are drawn to scale. So whatever we measure here, I think the scale used is 1 centimeter to represent 5 centimeter. So meaning whatever we measure here will be multiplied by 5 to get the real value. So the real experimental value. So now measure and record the value of M and P. Measure and record the value of M and corresponding value of N. So evaluate N inverse. So we are also searching for N inverse, which will be what? Centimeter per centimeter. So evaluate N inverse in each case, then tabulate your reading. So let's take that first. So let's go and take our values for M. For M, the first M, that's M1, we come from here to here. So we have this. So here I have 3.4. So that will be 3.4 times 5 according to the scale. That gives me 17.00. So I have the second one. So let me place it here. The second one is measured 5.2. 5.2 times 5 is 26.00. So the third one, that's 7 exactly. Okay, no, that's 7.1. 7.1 times 5, that gives me 35.50. So then I go for the fourth one. Make sure you avoid parallax error in making use of this meter rule or ruler. So we have 8.8. We have 8.8. So 8.8 times 5 gives us 44.00. So then we have the fifth one, which is 10.7. 10.7 times 5 gives us 53.5. 50 in 2 decimal place. So then we have the last one. Then we have 12.5. 12.5 times 5 gives us 62.50. So let's find the value of N. The value of N will be ranging from here to here. So we have, let's pick it from here to S1. So we have, this is 9.8. 9.8 times 5. The scale which is used there is also, so we have 49.00. So we go to the second one. We can still maintain our ruler till we take all readings. So we have here, this is the S2, we have 6.5. 6.5 times 5, that gives us 32.5. 32.50. So from there we have our S3, and that gives 4.7. 4.7 times 5, that gives us 23.50. So then we have our fourth value, which is 3.5678. 3.8 times 5, that gives us 19.00. As we can see, to show that they are both directly proportional, according to our table, one increases as the other one what? decreases, that means they are inversely proportional in terms of measurement. So we have the next one, which is the fifth one. We have 2.7 times 5, that gives us 13.50. So lastly, we have 2.4 times 5, that gives us 12.00. So these are the values we have taken from our readings. So let's evaluate n inverse. So n inverse, when you evaluate, should be in 3 decimal place. So we have 1 all over 49.00, so that gives me 0.020. Then we have 1 all over 32.5, that gives me 0.0307. So I have 1 all over 23.50, that gives me 0.042, or that's 43. So 1 over 19, that is 0.053. So then I have 1 all over 13.50, so that gives me 0.074. Yes. Then I have 1 all over 12.5, so that gives me 0.080. So these are the values we have gotten from our diagrams. So from there we are meant to we have tabulated the readings. So plot a graph of n inverse on the vertical axis. So this will be on the vertical axis and n on the horizontal axis. So let's do that straight away. On the vertical axis, I'm plotting my n inverse. So which scale is best used? So graph of n inverse against n. So I can also title it on my graph. In the examination, all these will be on the graph. So which scale is best used for my vertical axis? So if 2 centimeter represents 0.1, if 2 centimeter is to represent from here to here is 2 centimeter, so if I use that to represent 0.1, so that means that we have 0.1 divided by 10. So meaning each box is 0.01. Okay, and that scale will be too big, so I won't be able to cover my graph. So let me say 2 centimeter to represent 0.01. So meaning 0.01, I have on my vertical axis, that's on the n inverse axis, I'm using 2 centimeter to 0.01 centimeter. So it's per centimeter, I mean per centimeter. So on the horizontal axis, which is the m axis, I'm using 2 centimeter to, let's look at the table so we'll be able to get it well. So we have 17, 20, so it's a range between 17 to, let's say, 65. So how will I choose my scale? So if we choose 10, 20, 30, 40, 50, 60, 70, this is, I think, from here I have 10, 20, 30, 40, 50, 60. So that has not covered enough, or we could manage that. So if we have 10, 20, 30, 40, 50, 60, 70. Okay, let's make use of that. At least we've covered 70% of the graph, or let's say 68% of the graph. So let's go with that. So we have, I'll plot my graph. This is how many values? 1, 2, 3, 4, 5, 6. So if I use the scale of 0.01, let's start from here. 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09. So let's use this. Let's use this. So taking it from there, we have so the origin is 0, 0. So here I'm going to have 10.00, 20.00, 30.00, 40.00, 50.00, 60.00, and 70.00. So it has covered up to 60. So since I use 2 centimeters to represent 10 units, that means each small boxes is going to be 1. So from here I will have 0.01. That means each box is 0.01 divided by 10, and that gives us 0.001. That happens to be the value of one box. So from here we have 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09. So don't forget the units. So I'm having per centimeter here. No, I'm having per centimeter here, and I'm having centimeter here. That's the graph we're plotting. So let's look at how we can fix the values. So we have 17 goes for 0.02, and don't forget this is 0.02 counting from the origin to this last box here, and that goes for 17. So this is 10, 20, 11, 12, 13, 14, 15, 16, 17. So I pick that to 0.02 dot. Then I have 26 go for 0.03, 0.030, or let's say 31. So I can put it as 26. This is 21, 22, 23, 24, 25, 26. So that goes for 0.031. This is 0.031. So I can place that here. Then I have 35.5. 35.5. This is 35. 35 is this 31, 32, 33, 34, 35. So 35.5 should be around this region, and that goes for 0.043. 0.043. This is 0.04. 0.043 will count 1, 2, 3. So it's going to be on this line. So then I have 44 goes for 0.053. This is 41, 42, 43, 44. 44 goes for 0.053. 0.053. 1, 2, 3. This is 0.053. Then we have 53.5 goes for 0.074. 53, 51, 52, 53, 53.5 around this region goes for 0.074. 0.074. This 1, 2, 3, 4. That's 0.074. So then we have 62.5 goes for 0.08. 62 is 61, 62, 62.5 goes for 0.08. So which is this? So now how will I choose the best fitted line? The best fitted line should be, that means my graph should have moved up a little bit so I would be able to cross that line. So how do we pick it up so we the ones that are not going to pick will be distributed across. So we're going to have this, the best fitted line. This is 1 2 3 1 2 3. So we're going to pick this. I think this 3 will go with the line properly. So this is the graph we derive, 3 points on it, and the remaining are distributed across 2 here, 1 here. I think we are still good to go on that. So we are meant to determine, after plotting the graph, we are going to determine the slope S of the graph. So how do we determine the slope S of the graph? So let's pick from this point, from a known point. Take it down to this point. So here we have change in n arc, n inverse, then change in m. So the slope is going to be change in n inverse over change in m. So slope of this graph is going to be change in this. So we have 0.08 minus 0.03. all over, I have, this is 1 2 3, that's 63.0 minus, so this is 1 2 3 4 5, so this falls around 25. Yeah, 25.5 or 26.5. So let's see, 25.5. This is 1 2 3 4 5. So that's around 25. Let's say 25.5. So if we calculate that, here we're going to have 0.05. So, and we're going to have 63 minus 25.5, that gives us all over 37.5. So dividing that, so we have slope equals 0.0013. So this happens to be the slope of our graph. So from there we have determined the slope, and that is the end of the usage of the graph. And we are meant to take 2 precautions. We are meant to state 2 precautions you would take to obtain accurate results if you were to perform this experiment in the laboratory. If I had to perform this experiment in the laboratory, I would ensure that the lens is placed in the proper position. I would ensure that the image, or let's say the lens, is focused on the screen properly. I will ensure that there is no obstruction in the view. I mean obstruction that might lead to what? To getting wrong information about the distance, and placing of the distance correctly from the principal foci P is very, very responsible. And in measuring the length, the distance of the principal foci, I will avoid parallax error in making use of my ruler or meter rule. So those are the precautions that might come in place in the experiment. So then we also have state 2 applications of converging lens. Converging lens are used in are used by opticians, or are used to prevent or to correct short-sightedness. That's long-sightedness, to be precise. Long-sightedness. So that's convex lens. It is used to correct long-sightedness, and it is also used in some in binocular. It is used in binocular. It is used in some microscope and telescope or magnifying and so on. It is also used as magnifying lens in biology lab to view majority of things, that is smaller objects. So that is the use or application of converging lens. So we also have question B that says an object is placed 10 centimeters from a converging lens. So that is the object distance U is 10 centimeters. When a plane mirror is placed vertically behind the lens, the image form coincides with the object. The image form coincides with the object, meaning they meet, so meaning they have equal distance. Then calculate the focal length of the lens. Focal length F of the lens is question. So using the formula 1 over F equals 1 over V plus 1 over U, we could achieve this. So that would be 1 over F equals 1 over 10 plus 1 over 10. So which I would have 1 over F equals 2 over 10. So meaning F is equals to what? 10 over 2. F will be equals to 5 centimeters. So this marks the end of this particular experiment. Thank you for watching. Please subscribe to our YouTube channel. It's free.